So we were discussing a framework to handle nonlinear elements in a network. We were discussing the framework in the context of a diode, but then we shifted to any arbitrary nonlinearity. The framework that we're discussing was as follows. Let's say I have a simple network where one element is R, the other element is some nonlinear element. And let's say this is V in, this is R. And so essentially what we are trying to discuss is how do I get a solution for this network? And in the context of I want to understand what this output V0 will be across this generic nonlinear element. And this then we further said that if we know a priori what is the current voltage relationship of this nonlinear element, that is, if this is VE, the current through it is IE. If we know a priori, which we almost always know, because if we don't know the characteristics of the nonlinear element, then there's no point using it in the first place. If we know that, let's say VE is some f of IE, right? So then we said that there is something that we can do. There is no generic solution for such a case, but there are some approximate solutions. And the approximate solution comes in order to arrive at the approximate solution, you have to follow a two-step process. First step is find out, let's assume we know the current and the voltages through the mesh for some fixed value I1 when the input V in is applied, right? So that, let's say we know by using our nonlinear calculations or numerical approximations or putting it in a simulator. And let's assume that after considering all these things, we have gotten some values across the nonlinear element and through the nonlinear element. And we use those values to write out the KVL in this case. So in this case, it will be V in should be equal to I1R plus V0, where V0 is f of I1, right? So then we said that we can put in the effort to find this one. But now if I tell you to find what's going to be the new I and the new V in the network for a slightly different value of V in, right? I perturb the system with a voltage source and I change the value of the voltage source to some extent. Then how do we come to know what the new values of currents are, right? So, I mean, one obvious solution is to say that we do the entire thing again, but doing the entire thing again defeats the purpose of what we are wanting to do. So then what we saw is that Taylor series is of help. So for small perturbations, in fact, for any perturbation, we can simply write that if we change this V in to V in plus delta V, if we change this V in to V in plus delta V in, then we can definitely say that the current will change. If the current changes, we denote that change in current as delta I1 times R plus f of delta I1 plus delta I1. So till now, no approximation. But now, if we say that the value of delta I1 is such that I can approximate this guy with the first term and the second term in the Taylor series, right? So it essentially means that if I know the, let's say V2I characteristics, not IV, V2I, because it looks like the independent variable is I. And we say that the V2I characteristic is somewhat like this. Then if we know where we are, right? If we know where this I1 V1 is, and we say that we are interested in a small portion of the curve, right? Around in the vicinity of V1. So essentially what we are saying is if I draw a tangent around V1, and we are only interested in this small portion around V1, right? So in that case, it is arguable that if we don't deviate too much, what is too much is a different matter, but if we don't deviate too much from this original point, then it is possible to replace this curvy line with a straight line within that vicinity. Okay? That's all the Taylor series, neglecting of higher order terms in a Taylor series means. So if we do that, then we can approximate this. Now this becomes an approximation. This remains I1 plus delta I1R. And the other term becomes the original point where I was plus where I am going to if the velocity would be constant, right? In the case of somebody driving a vehicle. And higher order terms which we'll neglect. Right. So, right. So now what is so great about this? The great thing about this is that I can subtract this equation from this equation, and what we essentially get delta V in is equal to delta I1R plus delta I1 F prime I1. So this is nothing but saying that this is equal to delta I1 R plus F prime of I1. Now, this is a profound format because now it seems like, assuming F prime is real, this seems like if I have to draw a network for this equation, this network would look like I have a voltage source of value delta V in. This R remains as is, and the nonlinear element which was present here the nonlinear element that was present here got replaced by a resistor of value F prime of I1. Right? So now, why is this profound? This is profound because this guy I can solve without any problems, right? We are used to solving linear equations, and let's say there are frequency dependent components on this, then we know how to use Fourier transform, Laplace transform, those kind of scenarios. Everything, all signal processing that we have done or will do in the future will be almost always consist of linear analysis. So looks like now we have a framework to come from a generic nonlinear element in the network to a perfectly linear network, right? Make sense? Okay. So now one might say that, okay, fine, but is it possible to use this? So let me throw the question at you. So we know that this is the approximation. This is an approximate network. These are not equivalent, right? These are approximate networks in the incremental sense. If I have to go. So by the way, this term incremental we are going to use quite often. It's basically denotes the fact that if there is an increment in any perturbation, if there's an increment of any voltage or current in the network, what's going to happen to the original network? That's what we call it as incremental network. So now if we have to go from the circuit on the left to circuit on the right, is it, if somebody comes up and tells you that, hey, I found out this guy once, and I arrived at this network once, and now I can solve for any values of currents and voltages in the network. Will I be correct making the assumption, or will I be incorrect? Let me repeat the question. So it seems like if we start off with this network, right? We told that generic solution is not possible. So we found one solution, putting a lot of fight, right? I1, V1, blah, blah, blah. And then we said that you have a unique way of arriving at any other incremental values, right, around the around I1 V1 by simply going from the circuit on the left to the circuit on the right. Right. So let me give you an example. So let's say I have said that V in, let's say, is 1 volt, R is 1 kilo ohm, and analyzing the nonlinear currents and voltages, I found that for this operating condition, we have a V of, let's say, 0.5 volt and current of 1 milliamp. So this I have found using nonlinear methods. So now I tell you that, tell me what's going to be the currents and the voltages in this network when V in is 1 volt, 1.1 volt, let's say. I change it to 1.1 volt. What are you going to do?
You find delta I1 will be the incremental net because the change is very small.
Great, right? So essentially then I am supposed to be knowing everything about the right-hand side network, right? So what do I know? Let's start from delta V in. What will delta V in be in this case? 0.1, great. What will R be? 1K, no change. What will this guy be? This guy will depend on what the current voltage characteristics was around what? Around I1 of 1 milliamp. Right? So for this, you will need the information of what VE IE was. Maybe the curve goes like this, and you plot out whatever the VE IE was. In this case, it's given, it will be 0.5 volt. And then from here, you figure out what the F prime of I1 or F dash of I1 will be. It looks like in this case, it will be negative. So in this case, F prime I1 will be a negative resistance. That's fine. Incrementally, you can have negative resistance. That's not a problem. But now, this new circuit I can solve for without even blinking an eyelid. So that's great. Now, my question to you is, okay, so now, I mean, I'm jumping ahead of myself. So let me finish the thought. So let's say I found this, and I found that this guy, this F prime of I1 around 1 milliamp gives minus 100. Minus 0.1 kilo ohm, right? So what will be the current through this loop? What will be delta I? 0.1 by 1K minus 0.1K, that is 0.9K, that is 1 by 9 milliamps, right? So what will be now if I go back to the original network, if I go back to this network, what will be the total current after I have applied 1.1 volt? Yeah, so 1 milliamp minus 1 by 1, plus 1 by 9 milliamp, right? So basically, this is the original current was 1 milliamp. I will add 1 by 9 milliamp that I found from the incremental network. So whatever there was originally plus whatever is the increment is the new total, right? Great. So now if I tell you that this is a great framework, what I will do is I'll use it for everywhere, right? So let's say I change V in to 10 volts. So I'll use the same framework. I'll go here. Delta V in seems to be 9 volt. This becomes 9 volt. This was 1K. This was 1K. This F prime of I1 was 0.1 minus 0.1. This becomes minus 1K. And I will solve it again. Will I be correct or incorrect? Why? Right. So now whether I'll be correct or incorrect depends upon whether this F prime of I1 has changed when I have gone from 1 volt to 10 volt, right? Therein lies the question. If the answer to that is yes, it hasn't changed, then you would be right. And can you give me an example where the slope doesn't change? of any element, register. A perfectly linear element, slope never changes, so it doesn't matter. I mean, if it's an R by R network, I can have delta V into 100 volt, 1000 volt, million volt, doesn't really matter. This incremental network is always valid if you find out the case for one particular condition. Okay, but in these cases, you will have to justify if you have actual nonlinear network, for what value of increment things are valid, the incremental network is valid, you'll have to be slightly careful, right? Okay, any questions? Yes. Right.
If we take some ground at some reference in the lower class,
Sure.
then do 1 volt, and then the potential difference across the resistance is 1 volt. So would there be 0 potential difference across?
Why would you say 0 potential difference? This I didn't understand. Oh, okay. That's okay. The way I have drawn the current, right? Yeah. So yeah, thank you. So this is the problem of not paying attention on my end, right? So this, yeah, let me repeat his point. Some of you might have already noticed this. So it looks like I have one volt drop across this. Then since this is also 1 volt, then the potential across that nonlinear element should be 0, which is in fact correct, right? So I should have probably said that instead of 1 volt, this is maybe 1.5 volt. Then only you have 0.5 volt there, right? Yeah, thank you for correcting this. So let me change this also. 1.6 volt. Yeah. Okay. Yeah. Yeah, glad that you were awake. So yeah, so now this gives us a framework. Now this gives us a framework to figure out increments around around a known IV point, and this known IV point is called operating point, right? It's called operating point or quiescent point. So these are terms that are regularly used in these domains. We'll also be using this. So this is called. So let me write out the definition also. The IV points around which sketch the incremental network is called operating point or quiescent point, or often called Q point. Okay, and the incremental network, when you neglect the higher order terms, is called a small signal network, right? Or this is called a small signal analysis. What does small signal mean? In this case, small signal means that the perturbation should be small enough so that I can neglect the higher order terms. In the example that I gave, I assume that 0.1 volt perturbation is small enough without really justifying as much. But let's assume if that is small enough for which we can neglect the higher order terms, the network on the right-hand side will be called a small signal network, right? Or then the analysis, corresponding analysis that we are doing in the small signal network is obviously called a small signal analysis. Okay, so this small signal term will keep on repeatedly coming. So you'll be, I hope you'll get used to it. Okay. So let's do a rough example using a nonlinear element that we are familiar with, like a diode, and then hopefully it will drive home the point. So let's say we have a same network with a diode. Let's assume that I have applied 1.7 volt here. This is, I don't know, maybe 1 kilo ohm. And like we said in the previous class, for a range of currents, right? For a range of currents, we can approximate the diode with some fixed voltage, right? That's a numerical calculations, that approximation, numerical liberty that we take, but with the understanding that it's not entirely accurate, right? So let's say you have done this using numerical calculations and all, or put it in a simulator, and you found that if you hook up a diode like this, you end up with 0.7 volt across the diode. Okay, this is numerically gotten, right? Nothing fancy about this. You have gotten it numerically. And in this case, obviously, the current is 1 milliamp, right? You can find out from across the resistor. Either terminals of the resistors are 1.7 and 0.7, so the current is 1 milliamp. Maybe I am sitting somewhere here. So this is 0.7 volt, and let's say this is 1 milliamp. Okay. So now the question is, I raise this 1.7 to 1.8. So that is, I raise it to plus 0.1. So now walk me through the process. What should I do? What should be the incremental network? So let's start with the battery. What will the battery be? 0.1. Great. So this becomes 0.1. What will the resistor be? 1K. So what will I replace the diode with? So that's the question, right? What will I replace the diode with? So to replace the diode, what do I need to do? I need to find the derivative around the operating point in the IV characteristics, right? So before I dive there, so let me make one more point, which I missed a couple of minutes back. So normally, so this derivative that we see, that it's f prime I1 is essentially what? So when we do f prime I1, this is essentially del V del I, right? Around the operating condition of I1 V1. But as it turns out, in most cases, not most, almost all cases, you don't get a VI characteristics. You almost always get an IV characteristics. That's how the characteristics are measured, where V is the independent variable, I is the dependent variable, right? So since you normally always get IV characteristics, we typically then say that we represent this as del I, 1 over del I del. Right? So nothing fancy about it, but this is something you'll have to keep in mind. Okay. So a live example of that is the diode, right? So in case of a diode, we know the IV characteristics. And what is IV characteristics of a diode? I is IS e power. In a forward bias condition, I can simply say that this is VD over VT, right? As long as VD is much greater than VT. And in this case, do you think the example that we are taking, is this neglecting -1 valid? Well, let's assume VT is approximately 25 millivolt. What is VD in the context of our circuit? 0.7. So is this, can I neglect the -1 term? Yes, no problem at all. So if that is the case, so now this guy should be replaced with a resistor. What will the value of the resistor be? Or what will the expression of the resistor be? So help me out. What should I do? So this, let me call this RD. So RD will be 1 over derivative of this. So this is IS over VT e power VD by VT, right? So this is again a beauty about exponential, it keeps on repeating. So IS e power VD over VT is essentially the original I1, right? So this becomes 1 over I1 by VT, or in this case, this becomes VT by I, right? So we know what VT is. This is 25 millivolt. And we know the operating condition under which we are evaluating this circuit. What is I1? 1 milli. So this becomes 25. So this RD becomes 25 ohms. So if that is the case, what will be the incremental current? What will be delta I? So that is a piece of cake. So delta I becomes 0.1 by 1025, right? Volts, and this is amps, right? So we multiply it with this is amps, right? Yeah, this is amps. So if that is the case, what will be the new I1? New I, you add up 1 milliamp to this, whatever you get is your new I, right? So now the question is, with the question that we avoided when we are doing genetic nonlinearity is, how do I know that this incremental model is actually honoring the small signal limits rather, right? So we said that if you just increase V to increase delta V to a very large value, it's not going to work. But how do I know 0.1 volt is large or small? So what should I do to establish or to figure out whether this 0.1 volt is large or small? Yes, we have to find some error. So can you suggest a way in which I can find the error? When I say suggest a way, what I'm asking you is, can you tell me which element or the current voltage characteristics of which element will not hold if I make an error in this network? Resistor will hold, right? This is the perfectly linear element. So in case of a diode, I approximated the diode. So if something can go wrong, it should go wrong with the diode, right? So we need to establish whether under what conditions I can approximate the diode as a resistor, right? Make sense? So that we can figure out, because that is not a very difficult thing to figure out, because we know the current voltage characteristics of a diode, which is Is e power Vd over Vt. We do a Taylor series expansion over this. Let's take the full one. So if we do it, so let's say we want to do it around some operating point of Vd1, or in this case 0.7. So what will I do? What should I write? What should I write? I want to, so let's say I want to find out I plus delta I for this case. Let's say I neglect -1. So what should I write? How should I write out the diode equation? Help me out. Okay, so the Taylor series expansion of exponential e power x. What is this? Blah blah blah, right? So essentially, all we have to ensure is that if I have a delta term, right? So this will be, if we expand the diode equation around Vd, we'll get something plus some delta. So this, in this case, your delta will be, in case of x, we can put in the delta, right? So if we have, let's say the diode voltage changed by delta V, or delta Vd. So all we have to ensure that for a case, for the Taylor series to be approximated as these first two terms, like this is the quiescent in this case, I'm expanding around 0, right? In this case, the assumption is that I'm expanding around 0, but you can as well do the expansion around any operating point. So let's say we expanded it around 0, and we found out that we want to have this first term, 1, which is the quiescent term, right? The operating term, and this second term, which is the first derivative, right? And I want to neglect all these guys. And if I have to neglect all these guys, we have to neglect all these guys with respect to the first derivative. So which essentially means that this will be valid as long as x is much less than, sorry, there is no x squared by 2, right? We have, right? Or we have, I forgot. What is the derivative of e power x? Yeah, we have. Fine. So x should be much less than x squared by 2. Correct? Sorry, greater than x squared by 2, right? Okay, so which essentially means that in this case, what is x? In our case, x will be Vd over Vt. Should be much greater than Vd over Vt whole square by 2, which means Vd should be much less than twice Vt. Correct? This is if we expand e power x around 0. If we expand e power x around the operating point, all this Vd will be, this Vd will be delta Vd, Vt will remain Vt. So this will be your condition for expansion around the operating point, right? So you can think of e power x is essentially expanding where the operating point is 0, right? So in case of a generic case where we have we are expanding around some generic Vd, so x essentially gets replaced by Vd plus delta Vd by Vt, right? So and you do the calculations and you end up with the case where delta, as long as delta Vd is much greater, less than twice of the thermal voltage, which essentially means how much? 50 millivolt. It is much less than 50 millivolt, we are good. Does that make sense? Am I confusing you? Okay, so if we know the limit, so now how do I go back and check whether the small signal analysis is valid for this network? So I have established the limit. So what should I check? Whether the limit is valid or not in this case. So how do I go about doing this? What should I check now? I need to check the change in voltage across the diode, or the incremental change in voltage across the diode. So what will be the incremental change in voltage? This delta I that we have gotten here times 25.
Yes.
Right? So this delta Vt will be 0.1 by 1025 times 25. So which is like 2.5 by 1025. I mean, if I say 1025 is approximately 1000, so this essentially becomes 2.5 millivolt. Right? So our constraint is you have to be much less than 50 millivolt. I mean, now somebody might say 2.5 is much less, somebody might say not, but at least we can agree that it is less. So whatever is much less depends on how much accuracy you want. But let's say this is much less. So in that case, our small signal analysis will be valid. Okay, so we don't have to consider higher order terms. We can limit ourselves to the first order terms and go ahead with the analysis. Make sense? Yes. Okay, good question. So her question is why are we only considering the first two terms and neglecting the other? So the answer to that is we are constrained by mathematics to deal with a generic nonlinear system, right? We don't have a framework to figure out how to solve a generic nonlinearity, right? So if you remember the example that I gave, a student went with the essay of a dog and it came as river in the exam, and he has to find out something to relate the unknown to the known. So that's what we are doing. We don't know how to figure out a generic nonlinear equation solution. So we are reducing the nonlinear equation to something that we know that is a linear equation. With the understanding that we are incurring some error. But we are essentially saying that as long as the error is negligible, we don't bother. Right? So how do I neglect? I have to neglect the higher order terms. So the original operating point is the first term, that 1 in this case, right? And the plus x. This guy was the incremental term, first order term, right? So, and if I neglect all the higher order terms, this essentially becomes the original term plus increment. And then I subtract this with the original from the original network, I end up with a perfectly linear incremental network. So now we are in the domain of what I mean. So we can now use all our linear circuit analysis tricks, KVL, KCL, whatever, and with all linear elements and go ahead and solve. So that's the motivation behind doing all these things. That's the motivation behind neglecting higher order terms. Right? Yes.
We also like taking an assumption that our assumption is valid. and find out the delta I1 and then compare it with I1.
Yes, you can do that. You can, yeah, that's a very good point. His point is, can we also say that, let's assume our assumption is valid, you find out delta I1 and you compare it with I1. Perfect. You can also do that, right? But that is one step ahead of why it is going to be valid, right? So that is a good point, because this is a very simple network where I have shown one resistor, one diode. Now you can have a complicated network with multiple nonlinear elements. Then how do I go ahead and solve it? So then do I go ahead and solve for each of these I1, delta I1, or each of these I1s? That is something that becomes a problem, right? But the issue is, if you have different types of nonlinear elements, you have to ensure that the approximation is valid for all of those nonlinear elements, right? So at the end, you have to go back and see whether the approximation is valid for each of them instead of doing it for the entire loop. But in principle, what you are saying is correct.